Hey there! In this video by Anderson Duran Tutoring, we'll be learning how to use L'Hopital's rule. Back when we discussed limits and continuity, we were given the most trouble when we were computing limits in indeterminate form, like the ones that resulted in 0 over 0 or infinity over infinity, just like this one that we'll see here. Usually what we did was look to see if we can factor anything or use some special rule that was given to us. And the thing is, we no longer need to do that because we can use L'Hopital's rule to save us time. So in this example, remember, if we were taking this limit as x approaches 4, if we used direct substitution, we noticed that the numerator, let's see, 4, that'd be 4 squared, that's 16, minus 16, that would be a 0 in the numerator. 4 minus 4, that is a 0 in the denominator. This is what I mean by a limit being in indeterminate form, just like that. And so what we looked to do was we looked to make some sort of simplification, because this limit was equivalent to the limit as x approaches 4. And what we did was simplify the numerator, noticing that it was a difference of squares, and we turned it into x minus 4 and x plus 4. And it's still all over x minus 4. Upon simplifying, because we know we can right here, x minus 4's cancel out. This means that this is equal to the limit as x approaches 4 of just x plus 4. And then at this point, we were able to plug in 4 to receive 4 plus 4 being 8. And so we were able to use this algebraic technique by simply factoring out the factor that caused that indeterminance, and then we were able to move on with our lives. However, there are situations where it'll take us a lot longer to do some sort of simplification. And other times, being given rules, me personally, I don't like using rules that are given to us that I don't know how to use exactly. For example, if we were shown the limit as, let's say, x approaches 0 of sine of x over x. When we were given that, we were told that that's just 1. That was a special limit. And yes, I did commit that same mistake earlier in the series. So what I'm introducing to you is L'Hopital's rule. L'Hopital's rule states that if you have a limit as x approaches a certain value, any real number, it could be anything from negative infinity to positive infinity. And if we take that limit of f of x over g of x, or some function over another, and we receive 0 over 0 or infinity over infinity, then what we can do, instead of looking to simplify, we can simply go ahead and take the derivative of the numerator and take the derivative of the denominator, and then take the limit again. So here's what I mean. Let's go ahead and take a second look at that limit, this first one here. We had the limit as x approaches 4, and we saw that it was indeterminate at first. Essentially, what L'Hopital's rule states is that we can go ahead and rewrite this, because it's equivalent to the limit as x approaches 4, take the derivative of the numerator, and take the derivative of the denominator. So the derivative of x squared minus 16 is 2x minus 0, or 2x. The derivative of the denominator of x minus 4, that would simply be 1. So we have 2x over 1. If we were to compute the limit as x approaches 4, we wouldn't receive an indeterminate. We would receive an actual number. And so if we were to plug in the number, well, that would be 2 times 4 is 8 divided by 1. Hey, that is still 8. And notice, these are the same. These are the same. And so I hope that starts making a little sense as to how L'Hopital's rule works, because here's the reasoning. As we approach a, or whatever value we're approaching, if we see that f and g approach 0 or they approach infinity, we can't essentially say what that limit actually is, because 0 divided by 0 or infinity divided by infinity, those are weird quotients. Because if we're looking at infinity over infinity, well, we got to ask ourselves, what type of infinities are these? Because it is possible for one infinity to grow faster than another. Although they do eventually approach infinity, we can say that the limit is equivalent to the rate, the comparison of the rate at which they approach infinity. And the same reasoning goes for 0 over 0. We know that they both approach 0, but what rate do they approach 0 at? And so that's the reasoning. If we receive an indeterminate limit, we can simply take the derivative of the numerator and denominator to receive the true limit after taking the limit again. And so let's not shy away from this limit over here, the limit as x approaches 0 of sine of x over x. Again, if we were to take this limit straight up, we would receive 0 over 0. Our special rule tells us that we'd receive 1. But again, if we plugged in 0, we'd get sine of 0, that's 0. X, well, that's 0 again. So this will be equivalent to the limit as x approaches 0 of the derivative of the numerator and denominator. So the derivative of the denominator, that's 1. The derivative of the numerator, that is cosine of x. And I think now we can go ahead and plug in 0. And if we do, that'll simply be 1 over 1, which would be 1. So again, we saw that this limit was indeterminate. We saw that the numerator approaches 0 as well as the denominator. And so what we can do is just compare the rate at which they approach 0 then. And that's what we did. 1 over 1, that was 1. And so this special trig rule for limits was proved. And so I'm going to reiterate this. When we use L'Hopital's rule, we have to take the numerator, the derivative of the numerator, and then the derivative of the denominator. We are not computing the derivative of the quotient, because then that means we would use the quotient rule. That is not what we're doing. We're simply comparing the growth rates of the numerator and denominator separately. So just want to make that very, very clear. And there are other situations where L'Hopital's rule applies as well. And these situations are when we have, 0 times plus or minus infinity. If we take the limit, we receive 0 times plus or minus infinity. If we have a limit that approaches 1 to the infinity power, 0 to the 0 power, infinity to the 0 power, and something like infinity minus infinity. Now, as I stated, the L'Hopital's rule only works when we have a quotient, when we have one function divided by another and we're taking the limit. We can always rewrite any of these forms that we see as a quotient. And here's what I mean. Suppose we're taking the limit as x approaches 0. And for this example, we have to say 0 plus. So as we approach 0 from the right. And we're taking this limit of x times ln x. So this is a product. If we were to compute this limit right out of the gate, we would see that x would approach 0. X is continuous on its own, so that would just be 0 multiplied by the natural log of x. If you know what the natural log of x looks like, just picture the graph. As we approach 0 from the right, we see that we are approaching negative infinity. And so we have 0 times negative infinity. So yeah, this limit is in indeterminate form. This is an indeterminate form of a limit. What we can do is we can go ahead and use L'Hopital's rule. But like I said, it only works for quotients. This is a product. But watch what I'm going to do. I can go ahead and take this limit, and I'm going to rewrite it as the following. I can just say that this product is the following. I can just say that this is ln x divided by 1 over x. Because if we were to go ahead and work this out, if we have some number divided by a fraction, we would just change the sign, so multiply, and flip x over 1, which is the same thing. ln x times x, or x times ln x, it's the same thing. So that's why we can do that. And so, if we were to take the limit as x approaches 0 of this function, we would receive, well, like I said, ln x, that approaches negative infinity. 1 over x, as we approach 0 from the right, that will be positive infinity. And so yeah, because we have infinity over infinity, doesn't matter if it's plus or minus, we still have infinity over infinity. And so this would be an indeterminate form. And so again, there's more that we can do. So with L'Hopital's rule, all we got to do is just take the derivative of the numerator and denominator. So then this means that the limit as x approaches 0 plus of the natural log of x over 1 over x is equal to their derivative. So the limit as x approaches 0 plus, or the derivative of the natural log of x, we should know by now that is 1 over x. The derivative of 1 over x, or the derivative of x to the negative 1 power, we can just use that power rule, drop the power, so that'll be negative 1 times x to the negative 2 power, because we subtract 1. Essentially, this is the same thing as negative 1 over x squared. And so yeah, I'll leave it just like that. That'll be negative 1 over x squared. Let me go ahead and just erase this so I can keep going forward. And so there we go. If we were to, approach 0, well, we see that we would have 1 over 0. That would approach infinity. 1 over 0, that would approach negative infinity. And so again, it looks like this again would be an indeterminate form. But here's one thing that we want to realize. It doesn't have to be as complicated as it is. We have a fraction divided by another fraction. So again, just like earlier, we can use keep, change, flip. So we have 1 over x multiplied by negative x squared over 1. So this means that this is equivalent to the limit as x approaches 0 plus. We have x and negative x squared, so we see that this power will bye-bye. Then we have a negative x over 1. And looks like we're done. So as we approach 0 of negative x over 1, that'll simply be 0. And so if you had a hunch about, a 0 multiplied by an infinity still being 0, in this particular case, we were right. And that's just in this particular case. We just need to see that L'Hopital's rule works for these situations to confirm that it works. And so yeah, in this particular situation, it did. So let's take a look at one more example in this introductory video for L'Hopital's rule. So suppose we were asked to compute the limit as x approaches, let's say, infinity of x to the power of 1 over x. So the limit as x approaches infinity of x to the 1 over x power. If we were to go ahead and use direct substitution with infinity, we would receive infinity raised to the 0 power, because 1 over a very large number is 0. And so, yep, this limit is in indeterminate form. How are we going to tackle this? That's the main question. We definitely can, by doing this. So suppose this function was y equals x to the 1 over x power. And what I'm doing is, I'm going to look for a way to rewrite this as a quotient. That's exactly what I'm doing, because L'Hopital's rule only applies for a quotient. So, looking at this, I'm going to go ahead and see if I can find a way. Whenever I see exponents, I usually like to think logarithms. Try to take the natural log of both sides. That way we can see if something will give. And sure enough, it will. Because if we take the natural log of both sides, we'll have the natural log of y equals the natural log of x raised to the 1 over x power. Up next, let's go ahead and use our properties of logarithms, noting that we can take this power and we can drop it down as a coefficient. So that means we'll have the natural log of y equals 1 over x times the natural log of x. And more specifically, we can go ahead and rewrite this as the natural log of x over x. Just because we have that 1 over x and we're multiplying, we can go ahead and do that. So because we have the natural log of y equals the natural log of x over x, well, this isn't y by itself. It really isn't. But I'm going to show you something really quick. This might be a little confusing, but just try to pay attention for the next couple of seconds here. Because if we were to take the limit as x approaches infinity of this function, of the natural log of y, well, if we took the limit as x approaches infinity of the natural log of x over x, notice ln of x as x approaches infinity would be infinity. X, that would approach infinity as well. So we can apply L'Hopital's rule, and that will be the limit as x approaches infinity of 1 over x over 1. And so then this limit would be 1 over infinity. That would be 0 divided by 1, which would just be 0. Now, this wasn't a solution to this problem, because what we're looking at over here is the limit as x approaches infinity of x over 1 over x. That was not equivalent to ln x over x. However, take a look at this. If we wanted to get y by itself, we would essentially need to make each side, or transform each side, to a base of e. So here's what I mean. I'm going to go ahead and work with this right here, what we had earlier. What we can do is make the base of each side e. So we would have e raised to the power of ln y equals e raised to the power of ln x over x. And so on the left side, e to the power of ln y, or e to the power of the log or the base of e of y, that's a property of logarithm. So that means that y equals e raised to the natural log of x over x power. So this limit over here is going to become very useful in just 1 second. because this is y now. This is y. We have defined this as y, and this is legit. So we can go ahead and replace this y with this one. They mean the same thing. So essentially, if we're taking the limit as x approaches infinity of x to the 1 over x, we are likewise taking the limit as x approaches infinity of e raised to the ln x over x. So with this crazy problem so far, remember way back when in limits with properties of limits, let's say we had, the limit as x approaches some value, and we had some parentheses raised to some constant power like 7, and this was like 2x plus whatever, some function in here, just some function. We can transform this. This is equivalent to the limit as x approaches a of whatever that was, or whatever that good stuff was, and then we can actually take this entire limit and raise it to the 7th power. And the reason for this is because no matter what this approaches, e raised to that power will still not be affected by the limit, essentially, because these are the only parts that have a variable. If this was a variable like x raised to the ln x over x power, that'd be way different. But the fact that e is a constant, the fact that this over here, this 7 is a constant, we can go ahead and not ignore them, but essentially bypass them and look at the variable portion of the limit only. So I hope that made a little bit of sense. Go ahead and review properties of limits if that didn't, because I fully explained it in earlier videos. So here, the limit as x approaches infinity of e raised to this power is equivalent to the limit as x approaches infinity of ln x over x. And so essentially we have e raised to the power of the limit as x approaches infinity of ln x over x. That's what this is equivalent to. And so one more time, let me go ahead and erase this. That way I can do it another way, a more direct way. That way we're not totally confused. So then again, the limit as x approaches infinity of e raised to the ln x over x power is equivalent to e raised to the power of the limit as x approaches infinity of ln x over x. And like we saw earlier, this limit right here, it really helped us because we saw that the limit as x approaches infinity of ln x over x was indeterminate, so we took L'Hopital's rule right over here, which was perfect because we found that that was 0. And so this is equivalent to e raised to the 0 power, since this limit is 0. And there we go. Anything raised to the 0 power, or any constant raised to a 0 power, that'd be 1. And so therefore, the limit as x approaches infinity of x raised to the 1 over x power is equal to 1. So let's go ahead and recap. What we did so far was just explore L'Hopital's rule. It's essentially an extension of indeterminate limits, because now that we have knowledge of what the derivative is and what it does, we can now use it and apply it to limits. So if we have a limit as x approaches any value, and we're taking the limit of a quotient, so let's say f of x over g of x, if by using direct substitution we would receive 0 over 0, or infinity over infinity, or some type of infinity over some type of infinity, L'Hopital's rule can be applied to figure out what the true limit is. And again, there are other forms of indeterminate limits, like receiving 0 times infinity, 1 to the infinity power, 0 to the 0 power, infinity to the 0 power, or infinity minus infinity. There are ways that we can manipulate these functions algebraically so that we can then view them in quotient form, or numerator over denominator. If we can do that, if we can get it into this form, then we can go ahead and apply L'Hopital's rule, because most likely we'll receive 0 over 0 or infinity over infinity. And that's pretty much it. All you need to do now is just continue practicing. That way we can really solidify it and know how to use it when we see it in exam time. So, until next time, go ahead and watch a couple more videos, practice, and master. We'll catch you next time.